Hello. In this video, we will be discussing order of elements, recall basic properties of orders of elements, see how they interact with a groupomorphism, and finally, in length, we will discuss how we can compute order of a permutation. Okay, let's start with recalling basic properties of order of elements. When we were discussing cyclic groups, we showed that order of an element G is the same as the cardinality of the group generated by G. So if the cardinality of the group generated by G is finite, then the order of element is precisely that one. If G is of infinite order, then that means all the powers of G are in fact distinct, and the group generated by G is going to have infinitely many elements. In particular, if I start with a finite group G, then the cyclic group generated by every element of G is going to have finite order, and therefore every element of the group G has finite order. Remember, order of a group is the same as the cardinality of the group. And this equality justifies the word order. So every element of a finite group has finite order. Now, the way that we defined and we got to the order was by using the homomorphism from this group of integers to the group G, which sends n to G to power n, and then we looked at kernel of this group homomorphism. We said that kernel of this group homomorphism should be generated by one element inside Z, because every subgroup of a cyclic group itself is cyclic. And from there, we deduce that this kernel should be D times Z when D is not 0. That is precisely the order of the element G. Now, alternatively, we can say the following, and that's the main thing that you should remember from order. So, order a finite if order if order of an element is D and D is a positive integer, so for a positive integer D, order of an element is D precisely when the following holds. G to the m is the neutral element if and only if this order, this D, divides m. This is what you have to have in mind whenever we talk about order of an element. Order of an element tells what integer powers of G give us the neutral element. So that's again the same as saying that what are the elements inside the kernel of this map. So going to the neutral element means that that integer is in the kernel of this map. So it's about, again, order of an element tells us that what powers of G are giving us the neutral element of the group. The answer is that M should be a multiple of the order. That's if and only if. So G raised to power the order is the neutral element, and that one is the smallest positive integer with this property. We also showed that order of G to the K is a divisor of order of G, and it is precisely order of G divided by the GCD of order of G and K. Now, how does order behave under a groupomorphism? So suppose F is a groupomorphism from a group G to another group H. Then, for every element of the domain, order of F of G is a divisor of order of G. And this is the case when order of G is not infinite. If it is infinite, it doesn't make sense to talk about divisibility. So here I'm focusing on the elements that have finite order. So suppose order of element G is D, is a positive integer D. In particular, that means G raised to power D is the neutral element of the domain. Because F is a groupomorphism, it sends the neutral element of the domain to the neutral element of the codomain. And therefore, F of G raised to power D is the neutral element of the codomain. Now, the next claim is actually very important. It's an important property of group homomorphisms. It is useful on its own. So let's try to understand it and pay attention to the equality. So the claim is that if F is a group homomorphism, when I apply F to a power of G, then I can switch the order. First, I can apply F to G and then raise it to power M, no matter what integer M I pick. So M is an arbitrary integer. Okay, let's try to prove this. I'm going to be slightly sloppy and do not make a rigorous argument using induction, but you see the gist of the argument. If M is 0, then G to power 0 by definition is the neutral element of the domain, which is E sub G. Now, because F is a group homomorphism, F of the neutral element is the neutral element of the codomain. But that is the same as F of G raised to power 0, because every element of the codomain raised to power 0 is the neutral element of the codomain. So if M is 0, I get the equality that F of G to power 0 is the same as F of G to power 0. Okay, so that's for M equals to 0. Now, what happens if M is positive? If M is positive, G raised to power M means that I'm multiplying G M times by itself. So it is G times G times G M times. Now I'm applying this group homomorphism to this product. Knowing that F is a group homomorphism, we can conclude that it preserves the group operation. That means instead of applying F to a product, I can multiply after applying F. So I apply F to G and then multiply F applied to G and then multiply F applied to G, and I need to do it M times. So I get F of G multiplied to itself M times, which is the definition of F of G raised to power M. So again, if M is positive, we get the desired equality. Now, what happens if M is negative? If M is negative, then I can think about it as negative M times negative 1. Then negative M is positive. So I have it like this. So it is G to the M is G to power negative M raised to power negative 1. This is the usual trick from going to negative power to a positive power. So instead of dealing with G raised to some negative power, I can write it as G raised to some positive power, the whole thing raised to power negative 1. Now, we know that because F is a group homomorphism, F of inverse of an element is inverse of F of that element. So this means I first apply F to G raised to power negative M, compute its inverse, and that's the same as applying F to this element. Okay, now what am I now? What is the advantage of doing this? The advantage is that negative M now is positive. M is a negative number, and therefore negative M is a positive integer. Therefore, I know that F of G raised to power negative M, because negative M is a positive number, I can put this negative m outside, and I can write this. Why did I do it like this? It should have been written like this. Then it is by the previous case, by the case that you did for positive integers. Now I can write this as f of g raised to power negative m. Because negative m is a positive integer, I can pull it out of f. I can write this as f of g raised to power negative m. Okay, now I'm raising this element to power negative 1, and that means that I'm working with, I can write it like this. It is negative m times negative 1, which is the desired number that we were dealing with. This is f of g raised to power m, as we claimed. So in any case, for m0 or positive or negative, we show that f of g to power m is f of g raised to power m. Altogether, we got the claim. Now I'm going to apply it in this case. I have that f of g raised to power d is f of g raised to power d. And that is supposed to be the neutral element of the codomain. F of g is a number. F of g is an element inside the codomain, and raised to power d is the neutral element. That means the order of this element should divide it. Remember, order had this property that order of g divides m if and only if g raised to power that number is the neutral element. Now g raised to power d is the neutral element, therefore order of this element should divide d. Order of f of g divides d. So that's it. And that's exactly what we wanted to show, because what is d? D is order of g. So altogether we deduce that order of f of g divides order of g. So that means order of f of g divides order of g. So again, one of the important properties of order is the following, that if g raised to power m is the neutral element, then order of g divides m. Okay, so this is one of the crucial, important properties of order. In fact, this is, if a positive integer has this property, then that number is the order. That is what this statement says. Okay, now we understood how order behaves sort of under the Groupomorphism. Now, as a corollary, we get how it behaves under a group isomorphism. So if F is a group isomorphism, then we want to say that order doesn't change at all. So in the previous example, we discussed it when order of an element was finite, but in this example, I'm going to discuss it in general. I don't assume that order of G is finite. Okay, so for the finite order, we can actually use the previous example and use the fact that F inverse is also a group homomorphism, and deduce that order of G should divide order of F of G and vice versa. Therefore, they are equal. Now here I'm going to give you an alternative method that works for elements that have infinite order as well. Okay, so what do we know? By the claim that we showed, by the claim that we proved in the previous example, we showed that f of g raised to power m is f of g raised to power m for every integer m. Now remember, these are elements inside the cyclic group generated by G. In fact, the cyclic group generated by G consists of all the powers of G. This is the smallest subgroup that contains the element G. Similarly, the smallest subgroup that contains f of G, the cyclic subgroup generated by f of G, consists of elements of the form f of G raised to some integer power. Now, that means when I apply f to some element in the cyclic group generated by G, I land in the cyclic group generated by f of G, and moreover, I get every element inside this group. So if I define f bar, because I'm changing the domain and the codomain of f, I'm using different variables. But at the end of the day, this is the same as f restricted to this subset. But I'm also changing the codomain. That's why I'm using this different notation, f bar. So f bar is essentially f. So when I apply f bar to an element of the codomain, I'm essentially applying f to that element. But because I'm changing the domain and codomain of f, I'm using a different value. So f bar applied to an element in the group generated by G gives me an element inside an element in the group generated by f of G. Therefore, this f bar is indeed well defined. It does give me something inside the codomain. Moreover, not only it's well defined, but it is also surjective. Everything here is going to be covered by some f, because everything here is of the form f of G raised to some integer power, and f of G raised to some integer power is f of something in the cyclic group generated by G. So f bar is a surjective map. Now, because f itself is an isomorphism, in particular it is an injective map. Knowing that f is injective, because f bar uses the same rule as f bar is also injective. It cannot send two different elements to the same thing, because f cannot send two different elements to the same thing. So f bar is injective and surjective, and therefore f bar is a bijection. One can also check that it is also a group homomorphism, but we do not care at this point. F bar is a bijection, therefore domain and codomain have the same cardinality. So cardinality of the cyclic group generated by G is the same as the cardinality of the group generated by f of G. But remember, cardinality of a cyclic group is the same as the order of the generator. And cardinality of the cyclic group generated by f of G is the same as the order of f of G. Now that these groups have the same cardinality, the same order, we can deduce that these generators have the same order. And that's exactly what we wanted to show. So an isomorphism does not change order of elements. Now let's use this fact, both the claim, this equality, and the fact that order doesn't change under isomorphisms. Let's use this for a particular type of isomorphism, conjugations. We have already discussed that every conjugation is an isomorphism. So if I give you x inside G and conjugate every element of G by x, then when I conjugate y by x and raise this to some integer power, it's the same as conjugating y raised to that integer power by x. And the order of a conjugate does not change. It's the same as order of y. Okay, let's again go through the details. We'll recall that conjugation by, why did I write y? So let's switch the order. I wanted to say conjugation by x. Let's recall that conjugation by x, I feed it y, and then we conjugate it by x, which means I'm sending y to x times y times x inverse. This is a group isomorphism from G to G. This we have checked in previous videos. We've seen this, that conjugation by x is an isomorphism from G to G, where conjugation C sub x of y is given by this. Now that this is a group isomorphism, I can apply this rule
Applying this rule, we deduce, let's write it over here, c sub x of y to power m is c sub x of y raised to power m. And that's exactly this equality. And we showed that the order doesn't change under an isomorphism. So order of c sub x of y equals to the order of y, and that's this equality. So we see that conjugation does not change the order. If two elements are conjugate of each other, then their order are the same. And we see that when I conjugate an element raised to power m, it's like conjugating that element raised to power m. So they switch together. These are both important equalities. Please pay attention and make sure that you know how to use them. Now that we know basic things about order of elements and how they behave under homomorphisms, combined with the fact that because of the Cayley's theorem, every finite group can be realized as a permutation group, we go back and pay special attention to permutations. We want to understand how we can compute order of a permutation given its cycle decomposition. Okay, so that's our next goal of this video, how to find order of a permutation given its cycle decomposition. Of course, the easiest case would be that when our permutation is a single cycle. What is order of an M cycle? Let's say I index this time by 0, 1, m minus 1, the elements that appear in the cycle. So sigma sends a sub 0 to a sub 1, a sub 1 to a sub 2, and we go to a sub m minus 1, and then a sub m minus 1 is sent back to a sub 0. I use the indices 0, 1, m minus 1 to remind us what? Integers modulo m. So I'm going to use addition modulo m in order to understand how sigma does act on these a sub i's, how sigma is applied to a sub i's. So sigma sends a sub 0 to a sub 1, a sub 1 to the next one, and a sub m minus 1 goes back to a sub 0. So a sub 0 is a sub 1 and so on. So each time that we apply sigma to a sub j, we are adding the index by 1 modulo m. So again, we add modulo m. That's why I used the indices starting from 0. Therefore, when I apply sigma I times, I'm sending a sub j to a sub I plus j. Again, I'm thinking about I plus j modulo m. So I'm looking at it mod m, and I'm asking myself, what is this index? What is the remainder of I plus j divided by m? And that would be the index that I'm putting over here. In particular, sigma to the I is the identity if a sub j is sent to a sub j. And that means sigma to the I is identity precisely when all a sub j's are sent to all a sub j's, and that means for every j, I plus j is congruent to j modulo m for every j. So again, that means I can cancel out j because I'm adding mod m. That's a group. Therefore, I get that sigma to the I is identity precisely when I is a multiple of m. So that happens precisely when m divides I. But remember, this is precisely how we define order of an element. So sigma to the I is identity, is the neutral element, precisely when I is a multiple of m. That means sigma to the m is identity, and m is the smallest such positive integer. Therefore, order of sigma is m. So order of an m cycle is m. Okay, that's an easy thing to remember. Order of an m cycle is m. So intuitively, we have this cycle. We are moving around this cycle. Each time I'm moving one step, so I'm sending this one step further. I'm sending it 2 steps after I apply twice. And I'm wondering, when do I get back? When is the first time that I get back? And clearly that is m. So order of an m cycle is m. Now what happens if I give you the cycle decomposition of a permutation, sigma? So I'm giving you a permutation sigma. I write it as product of disjoint cycles. So there are a bunch of fixed points for sigma. Those are not very interesting. I put them aside. Then I have a bunch of disjoint cycles, M1 cycle, M2 cycle, M3 cycle, M sub k cycles. So these are disjoint cycles, sigma 1 dot sigma k. And I want to understand what is the order of sigma. Now, what does that mean? This means I have to look at sigma to the L, and I ask myself, under what condition do I get identity? For what else? For what else do I get identity? Okay, so that is the question that I want to address. Now notice, when I give you an element, so when I say for what else do I get identity, that means I have to apply sigma to the L to some x, to some integer x, and I have to see whether or not I'm getting back x. Now, when I feed x, if x is one of these fixed points, sigma to the L is x no matter what L is. So these points are fixed points. Those are clear what happens to them under powers of sigma. For the other ones, I need to follow the flow. So if x is here, no matter where in this cycle, if I want to get back to itself, I need to go multiple of m1 times. Alternatively, I can say that when I start with some point over here, the way that sigma is applied to it is similar on what sigma 1 does to this one. If I go to the next cycle, I have to ask myself what sigma 2 does, how I'm rotating. So in either way, either points of view, you see that if I want to get this rule, that sigma to the L is identity, if I want to make sure that every point is mapped to itself after L step, then L needs to be a multiple of M1, because I want to make sure that every point in this cycle is mapped to itself. It should be a multiple of M2, because I need to make sure that every point in the next cycle is mapped to itself. It should be, and so on until I reach the last cycle. It needs to be a multiple of M sub k, because I have to make sure that every point in the kth cycle is mapped to itself. Altogether, I deduce that L needs to be a common multiple of M sub 1, M sub 2, dot, M sub k, and that's if and only if. If L is a common multiple of those numbers, then sigma to the L is identity and vice versa. Altogether, we deduce that the least common multiple of M sub i's is precisely the order of sigma. Okay, but let's go over these arguments a bit slower, make it a bit more formal, and make sure that we understand what's going on. So for every x in the support of sigma I in the ith cycle, the way that sigma is applied to x is the same as the way sigma sub I is applied to it. Because remember, when I'm in the support of sigma I, sigma of x is sigma sub I of x, and I'm not leaving this support. I'm still in the same cycle. So I can do it again and again and again. At the end, I get that for every integer, the way that sigma to the L is applied to x is the same that sigma sub I raised to power L is applied to x. This is true for every integer L and every point in the support of sigma sub I. Now, that means if I tell you sigma to the L is identity, I can deduce that sigma to the I, sigma sub I to the L is identity. And therefore, the order of sigma sub I should divide L, from which we can deduce that if I tell you sigma sub L, sigma to power L is identity, I can deduce that M sub I divides L for every I. Okay, now in one of your homework assignments, you've seen that if two integers divide another one, then the least common multiple of those two should divide L. In fact, you discussed this when those two numbers are co-prime to each other. In general, using Euclid's lemma, one can show that if M sub i's divide an integer, then the least common multiple of those integers should divide L. So altogether, we are taking this for granted. I'm not going over that proof. You can also use the unique factorization of integers to prove this. So altogether, we get the following, that if sigma to the L is identity, then the least common multiple of M sub i's should divide L. Now I want to show the other way around. Suppose the least common multiple of M sub i's divide L. Then we know all these cycles raised to power L are identity, because M sub I is one of these, and that one divides L. From there, I can deduce that because order of this element divides L, I can deduce that sigma sub I raised to power L is identity. Again, because order of sigma sub I divides it. Now, sigma sub i's are disjoint cycles. Because they are disjoint, they commute with each other. Because they commute with each other, I can take their product and raise it to power L. I can reorder them, and I can deduce that sigma, which is sigma 1 times sigma 2, that's sigma k to power k. I can reorder them and raise each one of these sigma i's to the power L and then multiply them. Because they commute, I am allowed to do it. If they did not commute, this is not correct. But when they commute, it is fine, and I can do that. Now, because all these elements raised to power L are identity, I have identity, 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 and the product of identities, composite of identities, is always identity. Altogether, I get that if the least common multiple of M sub i's divide L, then sigma to the L is identity. We have both ways. Therefore, sigma to the L is identity precisely when the least common multiple of M sub I is divided, which means order of sigma is the least common multiple of M sub i's. So if I tell you that a permutation is written as product of disjoint cycles, the first one is M1 cycle, the second one is M2 cycle, the last one is M sub k cycle, then order of this permutation is the least common multiple of M sub i's. Okay, let's see some examples how we can use this rule. For instance, let's say I want to find order of the following permutation. Sigma is given in this 2-arrow format, and that means that 1 is sent to 3, 2 is sent to 5, 3 is sent to 2, 4 to 6, 5 to 1, 6 to 8, 7 to 4, 8 to 10, 9 to 7, 10 to 9. And we want to find order of sigma. As we learned in the previous page, it's enough to understand a cycle decomposition of sigma. And to find a cycle decomposition of sigma, it's enough to follow the flow. So we start with 1 and we follow the flow. That means we ask ourselves, where is 1 mapped to? 1 is going to 3. Then following the flow tells us I need to understand where 3 is mapped to. 3 is going to 2. 2 is mapped to 5. 5 is mapped back to 1. So that finishes the first cycle. Next, I ask myself, what is the smallest number that's missing here? 1, 2, 3, there is no 4. So I write down 4. And again, I follow the flow. 4 is mapped to 6. 6 is mapped to 8. 8 is going to 10. 10 is mapped to 9. 9 is mapped to 7. And 7 is mapped to 4, back to 4. Now, is there any number missing? So there are 4 numbers here, and there are 6 numbers here. Altogether, I have 10 numbers. There is no missing number. So that's a cycle decomposition of sigma. Now, the first cycle is a 4 cycle, and the next one is a 6 cycle. Therefore, the order of sigma is the least common multiple of 4 and 6, which is 12. Therefore, order of sigma is 12. Okay, so you see how effective this method is. It's not easy to write down sigma, sigma squared, sigma 2 power 3, and so on till we get to the identity, because we have to do it 12 times. But using this method, we can quickly understand what order of this permutation is. Now let's go back to the same question. Now that we have written this cycle decomposition, let's try to understand whether or not the sigma is odd or even. So is sigma odd or even? We have written this as a product of a 4 cycle and a 6 cycle. Is a 4 cycle odd or even? This we have answered. We have answered that an m cycle is odd if m is even, and it is even if m is odd. So therefore, a 4 cycle is odd. So this is an odd permutation. This one is a 6 cycle. 6 is even, therefore, this is an odd permutation as well. I'm looking at we are looking at a product of 2 odd permutations, and therefore it is an even permutation. So sigma is an even permutation. Alternatively, I can use the sine function and look at sine of sigma. Sine of sigma is product of sine of these cycles. The first one is an odd permutation, therefore its sine is -1. The next one is also an odd permutation, therefore its sine is also -1. Therefore, sine of sigma is 1, which means sigma is even. Okay. Now, next example shows us that the way that we understood how to find order of a permutation can be quite restrictive as well. What do I mean by that? Suppose P is prime, and I give you an element of a symmetric group S sub P that has order P. Then what can I say about this? So what can I say about elements of order P in the symmetric group S sub P? The answer is that every such element is a P cycle. So you should go around like 1, 2, 3, P, and going back to 1, but maybe with different ordering of 1 to P. So the claim is that every element of order P in the symmetric group S sub P is a P cycle, assuming that P is prime. If P is not prime, this is not the case. For instance, in S sub 6, we have elements of order 6 that are not 6 cycles. Essentially, something like this is a 6 cycle. 1, 2, 3, 4, 5. This is inside S sub 6 and has order 6. Because the least common multiple of 2 and 3 is 6. So this statement is not true when P is not prime, but it is true when P is prime. Let's see why this is true when P is prime. So I give you this sigma, I tell you that it has order P. I'm going to look at a cycle decomposition of sigma. We know that it has a cycle decomposition. So suppose that sigma 1, sigma 2, dot, sigma k is a cycle decomposition of sigma, and assume that sigma sub I is an m sub I cycle. Okay, because these guys are disjoint, when I add m sub i's, I cannot get more elements, more integers than p. So this means, again, because these are elements of S sub p and they are disjoint, when I look at their supports should be disjoint, and the cardinality cannot be more than 1 to p. I mean, it cannot be more than p. Only elements that appear in their supports are integers from 1 to p. Therefore, the union cannot be more than that. They are disjoint. From there, I can deduce that summation of m sub i's is definitely at most p. Now, on the other hand, order of sigma is supposed to be p, which means the least common multiple of m sub i's is supposed to be p. In particular, m sub i's are supposed to divide p, but p is a prime number. That means every m sub I is either 1 or p. But remember, in a cycle decomposition, these cycles are not supposed to be identity. This means m sub i's cannot be 1. So this means all those m sub i's are supposed to be p. But how can that be? Because their summation is supposed to be at most p. I cannot have k at least 2. In that case, I have p plus p, and that cannot be less than or equal to p. From there, I can deduce that there is only one cycle. K is 1. And I have m sub 1, and least common multiple of m sub 1 is supposed to be p. That means m sub 1 is p. That's exactly what we wanted to show. So from here, we deduce that there is only one cycle, and that cycle has length p, and that means that sigma itself is a p cycle. That's exactly what we wanted to show. So an element of order p in S sub p, if p is prime, is a p cycle. Now, the next type of questions that we can ask is the following. What is the maximum order of an element in S sub n? But let's make it explicit. What is the maximum order of elements among S sub 7? Okay, so again, we are going to start with the cycle decomposition of sigma. We write down sigma as a product of disjoint cycles, and assume that sigma I is an m sub I cycle. Then order of sigma is the least common multiple of m sub i's, and by a similar argument as in the previous example, when I add the number of elements in the support of these disjoint cycles, I cannot have more than 7 elements. So this means that this summation is at most 7. Now, I can order these m sub. I'm interested in the least common multiple of these numbers. I can order them. I assume that m1 is the largest one, then m sub 2, and so on. I'm looking at integers. I want to add them, and these integers are at least 1, or are at least 2, because m sub i's are length of these cycles, non-trivial cycles. And I want to get at most 7. Why would be greedy if there is something remaining I can add to the list and make the least common multiple possibly larger? So that means I'm going to write down 7 as sum of non-decreasing positive integers, and then take the least common multiple and try to find the maximum of such least common multiples. Okay, let's try to do some of them, maybe not all of them. So one way of writing 7 as sum of positive integers is just considering 1, 7. So essentially 1, 7 cycle. The least common multiple would be 7. Or I can write it as 6 plus 1. The least common multiple would be 6. I can write it as 5 plus 2. Least common multiple would be 10. I can write it as 5 plus 1 plus 1. Then least common multiple of these numbers would be 5. I can write it as 4 plus 3. then least common multiple is 12, or 4 plus 2 plus 1, then least common multiple is 4. 4, 1, 1, 1, it's again 4. Now, these are all the numbers, the ways that we can write down if the maximum is 4. Now, if the maximum is 3, then the only integers that appear are 3 and 2, which means the least common multiple of those numbers cannot be more than 6. We already have 12 over here, so I can disregard the rest and say that the maximum is definitely, the maximum among these least common multiples is definitely 12. And here is an example. I just consider this 3 cycle and this 4 cycle in S sub 7, and the order of this is the least common multiple of the length of these joint cycles, which is 12, and that will be the maximum of orders of elements of F7, using the fact that order of an element, order of a permutation is the least common multiple of the length of the disjoint cycles appear in the cycle decomposition of sigma. Goodbye.